Good morning, teacher. Today I will present my project. It is about vehicle routing problem, and there is reinforcement learning based solution to this problem. So reinforcement learning is a type of machine learning where an agent interacts with an environment and gets punishment and rewards for his actions. So the key concept of reinforcement learning is an agent. It is a main learner and decision maker of the environment. He performs different actions and gets reward for his actions. Environment is a world where an agent performs his actions. Actions is choices of an agent, and the reward is a feedback from the world to an agent. So there are two main types of reinforcement learning algorithms. First one is a model-based one, where we create a model of the environment and then we interact with the model of the environment, and we have to know everything about this environment. And the model-free one, where we don't have to create a model of an environment, we just perform our actions directly with an environment without having the whole knowledge about it. So you can see it here. Today we will talk about Q-learning algorithm. Q-learning algorithm is a type of model-free reinforcement learning, where we are using Q values to understand which action is better to perform in a current state. It is very effective in a discrete worlds, and the main aim of this algorithm is to generate the most optimal policy for an agent. So, as I said, it's very effective in discrete worlds like chess, grid world, or old Atari games. We are using Q values, and it is in iterative method. We every time with every step we improve our policy. We improve the optimal policy. So the main components are the same, but we have the state. The state is the current position of an agent in an environment. Episode is an instance of when the agent reaches to the final state of the environment. It can be win or loss. And Q values, they are stored in a Q table. It's a matrix and it shows the performance of an action which will take in a current state. To update our Q table and Q values, we are using Bellman equation. It is an iterative equation. Let's briefly talk about it. So we have a Q value of an action A in a state S. We have two parameters, which is alpha and gamma. Alpha is a learning rate showing how much new information an agent will learn. And for example, if the alpha is 0, then it means that agent does not learn a new information. It will just perform actions according to his previous experience. And if alpha is 1, then it means that agent only considers new information which he learned just now. Gamma is a discount factor for new rewards. For example, if gamma is 0, then agent will consider only immediate rewards which he can get now. But if gamma is 1, then agent will consider future rewards which he will get in the future. And finally, we calculate the maximum Q value of the future state and future action. This algorithm has a dilemma. It's called exploration versus exploitation. An agent can study where he can get a reward, and he will always go to this place where he can get a good reward. But we are not sure that it is the best reward of the environment. And the agent, since it is getting a reward, he will not explore the world because he already gets rewarded. To solve this dilemma, I'm using epsilon greedy solution for a dilemma. This parameter can help us to control exploration versus exploitation. Let's see the pseudocode. Firstly, we generate a Q table and we pass to the function. And inside of the function, we generate a random value between 0 and 1. And if epsilon is bigger than a random value, then we perform a random action from our action table and we explore the world. Else, we just take the best action from action table from to exploitate the reward. So my implementation of this problem is a game written in Python using Pygame library. As the main aim of the game is just to park a car inside of the parking area, avoiding obstacles. Let's see the structure of my code. It's several files. Let's talk about the main Py. Firstly, we import all important libraries and files, and we initialize the important game-related variables, and then we create a map. After it, we create instances of the car parking, and we can create as much people, animals, and walls as we want, and then we are using this for loops for generate them and draw them on the map. So we have an action dictionary, and after it we just create some instances of counter, step counter, and controller. I will talk about them later. After it we create a Q value matrix. I give their map width and map height and add +2 because a map has borders which we cannot see, and if a car tries to escape the map, it will hit the border, and I need to punish the car for doing this action. So our metrics have to have extra columns and extra rows to act like borders. So, and then I'm passing the number of actions, which are 4. In the main game loop, I'm drawing the map and starting the counting of the steps. If artificial intelligence plays this game, I'm checking if a user closed the window or not. Then I get the state and choose an action. After it, I'm just handling the actions, I'm handling the movement of the car if artificial intelligence is playing. Then I'm rewarding an agent and perform again Q-learning algorithm. If the user is playing the game, then I'm just checking if the window is closed or not, and just checking which arrows he's pressing on the keyboard. In the end of the file, I'm just writing all important information inside of the terminal and creating a heat map to plot the history of the agent. In objects, I have a base object which is being inherited by all objects. Inside of this class, I'm generating a random variables for every object, and they have to be unique to avoid collision between obstacles. They are generated until they being unique. Then I have a parking class and I have a car class. Car class has methods which are allowing for movement and the resetting method. Then I have an obstacle class, and the obstacle class is being inherited by people, wall, and animals. I made it to make easy to make game easy modifiable. If, for example, I need to add something only to obstacles, I just can add it here without parking and car improvement. So logic Pi, it has step counter which counts the steps, and for example it checks the collision of this not visible borders. For example, if the car is spawned near to the border and car tries to go outside of the border, the coordinates of the car will not change because it cannot go outside of the border, but the step will increase. It means that the car tried to escape and I need to punish the car for this action. Then I'm checking the collision with the obstacles and getting history of the steps. In counter counts the successful parkings of my car, and it saves the successful parkings inside of the file. Then controller just handles the movement of the car. It calls some methods to handle the movement. Grid map just simply draw the whole map of my game and creates the map. Artificial intelligence.py gets the state of the car. It can be parked, wall collision, normal, or obstacle collision, and this method just draw the game inside of the terminal. Then we create a Q value matrix. As I said, we initialize it with zeros firstly. And in a Q-learning, we perform the Q-learning algorithm according to this equation. By the way, in the beginning of the file, we have we can define alpha, gamma, and epsilon parameters. Epsilon for this function, choose action. It solves the dilemma between exploration versus exploitation. So, and calculate reward function is very important. Firstly, I calculate the distance from parking to the car, and according to this distance, I have an exponential function. If the distance is bigger, then the punishment for the car is bigger too, because I need the car to be near to the parking. The same stuff I'm doing for the all objects on the map, all obstacles. So if the car is near to the obstacle, the car will get punished more because I want to avoid the collision. But if the car is far from other obstacles, it will definitely avoid the collision, so I don't give any punishment for the car. Also, I have extra reward for being a car near to the parking area. You can see it here. Last reward is when a car can see the parking area. For example, if it is located here, it can see the parking area here too. But if it is located here, it cannot see the parking area because obstacle is does not allow to see the parking. So firstly, I'm checking if inside of the list any object has the same x or y coordinate as my car. If no, then I'm saying that yes, we can see this parking area, and I'm giving extra 20 points of reward. This one, this is visual.py. It's file which I'm using for showing the heat map of the history of my car, where it has been. And it looks like that. For example, you can see here that if you change the epsilon value, the exploration area of the car also changes. As you can see here, epsilon value is small, so car always goes to parking like that. It does not explore the world, it's explode the current reward. You see, white, by the way, white objects means that car have never been here. But if epsilon is big, then car tries to explore the world. You can see that the car have been here a lot of times, and it's explored more world than previous time. I will show you how my project works. Firstly, I'm just controlling the game with arrows, and I can park the game. I can park the car or collide with obstacles, and every time the car restarts the game. But if I enable, just a second, if I enable an artificial intelligence, it will play the game by itself. You see, the game started to explore the world, and it tries to find the parking. After a time, it will find the most optimal path. Every time the car parks to the parking, it resets its own coordinates to spawn again to the initial position. As you can see, car found the parking area, and because I have a reward here, it tries to exploit this reward. And you can see it found the most optimal path. The pattern is like that. You can see it's like that. In the heat map we will see it. You can see. Let me open a heat map. And as you can see, initially the car was here. And you can see this pattern. You remember the car was going like that, right? So we can see it here. The car was going like that, and every time it was exploiting here. Pardon. So that's all for today. Thank you for listening. Have a good day.